We're going to discuss the polyatomic ion on this video. We're going to come up with some Lewis dot diagrams and then even bring in some formal charges. Nitrite's a polyatomic ion. You'll find it in the form of sodium nitrate, potassium nitrate. You'll hear about it typically in terms of foods. Nitrites, when put into foods like corned beef, will keep the foods to a nice bright pink. So if you've got a nice bright pink on your corned beef, there's been a little bit of nitrate added to it in addition to salt. Nitrites are also found naturally in all sorts of things. You'll find nitrites in celery. In fact, we will use celery powder instead of sodium nitrite to pinken up things and to cure them. Again, cured meats. It's used to prevent bacteria from growing and also keeping the meat looking fresh. But let's get back to what we're going to do here, which is come up with a explanation using Lewis dot diagrams to try and figure out what this molecule is like in terms of electrons, and we can use that really to sort of predict what they do chemically. Well, here we go. We've got nitrate, and you know the routine that we have for determining, making our Lewis dot diagrams is that our Lewis dot rules. We decide which atoms are bonded. Usually the least electronegative atom will be the central atom. We count all the valence electrons. Then we put 2 electrons in each bond. So let me get back to here. Here's my structure. We've counted our valence electrons. 5 for nitrogen. It's easy to count valence electrons. 1, 2, 3, 4, 5, 6, and 7, and then 8 if you include neon, argon, and krypton. But only argon and krypton make compounds, so we don't have to worry about that. Oxygen is 6, and we have 2 of them, so 6 times 2 is 12, and we have a negative charge. This is a negative polyatomic ion, and we come up with 18 valence electrons, an even number. That's what we expect. If you forgot this negative, you would have come up with 17 and said, something's wrong. Now, I've drawn the structure here. Nitrogen bonded to oxygen, bonded to oxygen. And no, but, this is a possibility. We've got 3 atoms. We can put them together. Now, we have 2 bonds. These lines mean that we have a pair of electrons in here. The nitrogen nucleus is attracted to these pair of electrons. The oxygen atom is attracted to these pairs of electrons, and in doing so they lower their potential energy, and we form a covalent bond. The same thing between these 2 oxygens. Now we've eliminated 4 electrons with 2 bonds, so we have to come up with 14 valence electrons. Our rule that we had was to place 2 electrons in each bond, and except for hydrogen, complete the octets of the atoms attached to the central atom by adding electrons in pairs. Okay, here we go. Add a pair of electrons to the surrounding atom. Here's our first surrounding atom, nitrogen, and then I'm going to add another pair of electrons and another pair of electrons. So far I've added 6 out of these 14. I'm going to take my other one, so we've got 8, and then 12, then 14, and then the remaining electron is, here we have 6 and 6 is 12, and our remaining leftover 2 valence electrons are put on the central atom. That's our rule. So we've used up all 18 valence electrons, and that's fine. One of the first steps in coming up with, when AP graders grade Lewis dot structures, they say, did they show the right number of electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. You'd get a point for that. They'd be very happy up to there, but we want to get the full credit for this. So let's pull up our other rule that we have here. If the central atom does not have at least an octet, if necessary, form a double bond. Well, okay, let's see. Double bond. We have our octet here for nitrogen, an octet for the oxygen, but we don't have 2, 4, 6, 8 here. But we don't have 8 electrons, so what we do is we take a pair of these electrons and slide them over to make a double bond. Now we could use those, or we could use this guy right here and slide that over there. Those are your options. Now I'm going to take those electrons And rather than do that, I'm going to end up picking up a double bond. And I've got one right here. In fact, let me pick it up right now. There it is. Copy. And then I'm going to paste it right here between the nitrogen and the oxygen. And indeed, now I have an octet around the nitrogen, 2, 4, 6, 8. I have an octet around this oxygen, and I have an octet around this oxygen. If you were asked to come up with a Lewis dot structure for the nitrite ion, this would fulfill the requirements, and you could get a full set of points for that. But there's some other options that you could have used. Now, that's what I want to bring up next, because you could have said, wait a second, I'm going to do this a little bit differently. I'm going to put that double bond here instead of between the nitrogen and oxygen and between these two oxygens. And this would be perfectly fine too. You could get full credit for that because you fulfill the requirements of a Lewis dot diagram. Right number of valence electrons, octets around everybody, and again, 2 full points. Or there's even this choice, but okay, this choice wouldn't be right because we've got a problem here because we don't have an octet around the nitrogen, and I've got to go back in and take that pair of electrons and put them into the center and then make myself a double bond. I'll just get rid of this, and I've got a double bond waiting to be put in right there. Made the double bond a little bit shorter than a single bond because with those p orbitals making that pi bond, the bond is shorter. Okay, I've got 3 acceptable Lewis dot diagrams here, but I mean, to make them really look good, you would end up putting brackets around them to indicate that each of these has a -1 charge. Otherwise, somebody looking at it independently would say, well, what's going on here? The electron count is off from what I read. So I'll put those in just so that things look about right. We've got our 3 choices, and as I say on FRQ, if you were asked to come up with the Lewis dot structure for the nitrite polyatomic ion, each one of these would be acceptable. One of these is going to be good. The other 2 probably aren't going to be likely. So which one of these things is the real nitrite polyatomic ion? Will a real polyatomic ion stand up? Well, the way in which we do this is we end up using something that's referred to as formal charges. And if on an AP exam they say, draw the nitrite ion with the correct structure based on formal charges, well, you'd have to do that. You'd have to figure out, well, here we go, formal charges. We've got formal charge gowns, we've got our tuxes, and of course we've got a formal dance, but we know it's not going to be that. There's another way of coming up with formal charges. Let's see what we're going to do. I have a set of rules that I put together on our sheet here that describes how to deal with formal charge. As you can see, they're a little complicated here and they're tough to remember. I think there's a better way of doing this, and let me show you that way. The first thing to do is, once you've got your diagrams, is to draw some circles. So I'm going to draw a circle around each one of these atoms. So here's our first circle. I'm going to put the rest in right now and start drawing them. Draw these circles. Make sure that you include half the bond. So there we've got 1, and we'll keep on going. Now fast forward. Okay, there's the circles. You could probably draw them about as fast as I could on fast forward if you had a piece of paper. Now that you've got these circles, you're really going to find it's going to be easy to do the formal charges for these, because you look within the circle of each one of these structures or whatever structure you've made, and you count the electrons in them. Like we have 1, 2, 3, 4. Now we've split this bond in half, 5, 6. So our electrons that we have here are 6 electrons. There's our 6 electrons, and that count was made. So just count the electrons in each one of these circles. Now we'll do the same thing all the way around. Okay, that was a fast count. I showed you I did the nitrogen here. Let me just do one more on this oxygen. We count 1 for this single bond, for this bond, 2, 3, 4, 5. 5 valence electrons. So that's done all the way across. As you can see, we've got quite a variety here. So let's start now for the last part of our formal charges. We know nitrogen, and nitrogen is here, and it's supposed to have 5 valence electrons. But here it has 6. This nitrogen is out of whack for its p subshells and numbers of electrons and the second energy level. You'd expect there to be 5 electrons, and it's got 6. So this gives us our formal charge. This said this one's out of kilter. It has one more electron that you would expect, and its formal charge is -1. Now, here we have our oxygen. We counted 5 electrons that it controls, but oxygen is supposed to, here we've got our Lewis dot electrons, is supposed to have 6. So the oxygen is missing an electron, hence we give it sort of a formal charge of +1. It's out of kilter because it's really missing an electron. It has a +1. And then this oxygen here has 7. So it has an extra electron. This has got our -1. Now, one of the things you can always use as a double check for your formal charges, and that's where formal charges are, up here, is your formal charges will add up to the charge of the molecule you're looking at. In this case, we have a charge of -1, we've got a charge of -1. If it's a neutral molecule, you have to add up to 0. If the total of your formal charges doesn't match your molecule, then you did something wrong. Well, let's keep on going. By the way, formal charges indicate that something's amiss. So you say, wait, this is not good. A -1, a +1, a -1. Everybody's messed up on this. These things don't have their lowest potential energies. So let's go for our nitrogen here. I mean, this is the worst ever we've seen, a -2. Somehow the nitrogen managed to pick up an extra 2 electrons, which is something we don't expect. And our oxygen here has a +1. It's missing an electron. It should have 6. And if we did things right, we'd expect everything to add up to -1. So my guess is this oxygen here indeed has a formal charge of 0. Formal charges add up, but a -2 and a +1, no. You want a formal charge that, no, that's wrong. So let's go here. Maybe this is better. Well, an oxygen here has a -1. It should have 6 electrons, and it's picked up an extra electron. Our nitrogen here, let's see, 5 electrons. Well, that's good. That's a 0. That's what we sort of expect. And if we did things right, this oxygen here, 6 electrons, 6 is what we expect is 0. So by far, this structure is our best because it has the lowest formal charges. Now, if you have a charge, you'd expect the substance with the highest electronegativity to have the negative charge. And oxygen has, it's the second highest electronegativity of all the elements. Only fluorine has more. So if anybody's going to get a -1, this oxygen is going to. So this structure here, the one that we end up having with the lowest formal charge, is going to be the structure that is the preferred one. This is what you'd expect the answer to be on an AP exam. It said, what is the best structure using formal charges? This is how you end up doing it. Now, this structure, if you look at it in terms of shape, has 1, 2, 3, a steric number of 3. 1, 2, 3. So we'd have a bent molecule with 120 degrees expected between these two. So here we've got our preferred structure of the nitrite polyatomic ion. Now, it's got a -1 charge, a double bond, and a single bond. Now, you'd expect this double bond to be shorter because of the pi bonding than this one. When you've got a double bond that could have been placed in either location, because we could have done this just as easily on the other side and had exactly the same formal charges. The 8, 8, and 8 is just that we've got the double bond here on this oxygen. So these two structures would be classified as resonance structures, where both would end up occurring. 1, 2, 3 groups of clouds of electrons around our central nitrogen. We'd have a bent molecule, most likely in the area of 120 degrees. but this is going to resonate between these two. So one oxygen, I mean, this p orbital is going to be just as comfortable here as there, and so it's actually going to be both places at once. And our bond lengths are going to be the same for both of these, a little bit shorter than a single bond and a little bit larger than a double bond. It sort of averages out. So here we've got our bent molecule, and this is one way of showing where this double bond is averaged between the two. So there we've got our nitrite polyatomic ion, finding out which is the best formal structure, the resonance structures, equal bonds, and there is our nitrite polyatomic ion. Very good.